Right, so now we're going to talk about an important class of probability distributions, which are the exponential family. Okay, so the exponential family has the following form. So it's a probability distribution at a point x with parameters theta of the form the exponential of theta I h I x plus k of x minus psi of theta. Okay. So x is your random variable. Theta sort of points, it's like on your information manifold, right? So it's an n-dimensional vector parameter. Okay. Which specifies which specific distribution you're talking about, right? H sub I of x, right, are n functions of x, which are linearly independent. And then k of x is, again, it's like a function of x. And then psi is chosen to be a normalization, basically. So basically psi is chosen so that if you integrate, it's like this probability distribution over, it's like the entire space of random variables, it's like it normalizes to 1, okay? And then here, it's like we're using the Einstein summation convention. There's a raised I and a lowered I. It's like, so there's an implicit sum over I. Okay. So, so we can introduce a new vector random variable. Let's call it x, which is x1 to xn. It's given by xi is hi at x. So in addition, we also introduce a measure. On the sample space. X. Okay. So let's refer to this measure as d mu of x. This is exponential of kx dx. Okay. So you can think of this k term here, it's like as a measure, okay, on the space of random variables. So when you do that, you can rewrite p, it's like dx, right, is in a different form. So let's see what happens. So with that, I can write px theta dx as the exponential of theta dot x. So x is this vector. It's like where I've evaluated the hi's. It's like the point x. So this is theta as before, and this is the x which I have here. That's going to give you this term minus psi theta, and then the kx exponential kx term. I'm going to put in this new measure d mu d mu of x. Okay. So by putting k it's like into the measure, I can say that p of x now is equal to this term involving exponential and this is a probability density function, but with respect to this measure. Okay. All right. So you have these probability density functions. It's like, and you have a family of them. So let's denote a set of these probability density functions as M. So M is the set of px theta. And we know that it is parametrized by the x's, sorry, by the thetas. Okay. So this is a n-dimensional manifold. So this forms an n-dimensional manifold. Where theta is the coordinates, right? Is a coordinate system. Okay. And then, if we recall, it's like we want to choose the psi so that it's a normalization. Okay. So this is a probability distribution, right? So we want the integral of p x theta d mu x to be 1. So this is the normalization condition. So this implies, right, by looking at this expression for p of x, that psi of theta is equal to the log of the integral of the exponential of theta dot x d mu of x. Okay, so this is a convex function. Okay, so It's called the cumulative generating function, or the free energy. This is the cumulative generating function in statistics. Or the free energy in physics. So, it's like by now, it's like you should know that if you have a convex function, right, then one natural thing to do is to take that convex function and then construct something like a Bregman divergence from this, okay, and then define this dually flat structure. It's like on that manifold, okay. So that's what's going to happen. So what this is saying is that if you look at the space of exponential probability distributions, it's like which we had just sort of discussed, right? Then the cumulative generating function, it's like on the free energy, is a convex function. It's like on the space, and so it defines it's like a Bregman divergence, and it endows by virtue of this Bregman divergence, you can endow it's like the space of exponential families with sort of this dually flat structure which we've been talking about. Okay, so given this free energy, right, we induce a dually flat Riemannian structure. On this manifold M, it's like which is the family, the exponential family. Okay. So and then the coordinates are theta, as we discussed, right? So the affine coordinates right, sort of are theta, okay, which is called the natural or canonical parameter. Of the exponential family. Of an exponential family. Okay. So, right. So if you recall, it's like there are basically two main things. It's like which you use. It's like to construct. It's like an exponential family. It's like there are these HIs which we had talked about, which are this family of linearly independent functions. It's like on the random variable space. And then there's the measure, it's like you endow, it's like the random variable space with, right? Which either equivalently defines mu or defines it's like this k of x term, which we had before. Okay. All right, so you have these affine coordinates. It's like that's the natural canonical, it's like parameters, it's like of the exponential family. And then if you recall, it's like once you have that, and the convex functions, it's like you can construct a dual set of coordinates via the Legendre transform, right? So the dual affine parameter right is given apply the Legendre transform. So let's call that theta star. It's just the gradient of this free energy function at the point theta. Okay, and you can check what that is. Okay, so which is the expectation of x. Okay. Okay, so eta. Okay, so this is the expectation of x. It's the integral of x px theta d mu of x. Okay, so this is also referred to as the expectation parameter. In statistics. Okay. So this is just the dual, it's like parameter system. So we can refer it to either theta star, it's like, or we can refer it to eta. Okay. So in place of theta star, we use eta. Okay, so eta is Legendre transform. Okay. So now you have two coordinates, theta, which are the natural coordinates. It's like, and then the natural canonical parameters. And then it's like you have the expectation parameter, which is the dual coordinate system. Okay. And as before, it's like, if you recall, if you want to get from eta back to theta, that's given by the Legendre transform of the dual of the original convex function. Okay, the convex dual. So let's see what that is. So we can denote this, the dual convex function phi star of theta star by psi eta, and this is equal to the extremum over theta of theta dot eta minus psi phi, theta. Right. So again, it's like, this is what you would do. For example, in mechanics, right? If phi was the Lagrangian, it's like, this is the thing you would do. It's like, in order to get the Hamiltonian. So the Hamiltonian is the convex dual of the Lagrangian via the Legendre transform. Right? So this is exactly analogous to that. Okay, so so let's compute what that is. So to obtain this dual convex function. So we first compute the negative entropy, it's like of the probability distribution. Okay. Okay, so this is given by the expectation of the log of p of x theta. So this is the integral of p of x theta log p of x theta d mu. Okay, and then this is theta times eta minus psi theta. Okay, so with that, you can check that this is the dual convex function. So the dual convex function phi star, phi is denoted by psi and is given by the negative entropy. Okay, where you regard theta is regarded as a function of eta via the Legendre transform. Okay, so if we recall, it's like one of the points of introducing the dual convex function is that Legendre transform of the dual convex function maps the dual variable back to the primal variable. So you get that theta is equal to the gradient of psi at eta. All right, so so the thing worth noting is that the dual convex function is negative entropy. It's like of the probability distribution. Okay, so one of the things it's like we had discussed, it's like when we first started talking about Bregman divergences, right, as a sort of interesting example, was that the KL divergence is the Bregman divergence associated with the negative entropy, right? So immediately it's like what you're going to expect to see is that when you work with the exponential family, right, then one of the natural objects, one of the divergences, it's like which is going to be associated with this, right, is the KL divergence. Okay. All right. So let's keep going. So the divergence from P of x theta prime to P of x theta, right, is given by d phi theta prime. to theta is equal to phi theta prime minus phi theta minus eta dot theta prime minus theta. Right, so this is one of the many ways it's like you can write, it's like the Bregman divergence. It's like, so this is just one of them, where we've written it in terms of this dual variable here. Okay, so this is going to be equal to the integral of p of x theta log p of x theta divided by p of x theta prime, okay, the mu of x, and this is of course just the KL divergence from theta to theta prime. Okay, all right, so as I said, it's like the divergence is related to KL divergence. And then once you have the divergence, there are associated, there's an associated Riemannian metric, okay? So the Riemannian metric is given by Gij theta is equal to partial respect to I, partial respect to j of phi theta, and then the inverse G super ij of eta is equal to di partial respect to I, partial respect to j component of psi, it's like eta. Okay, and then what we're doing here is that we're using some notation. D sub I is d theta super I, and d super j is d eta sub I. Okay? All right, so again, it's like whether you have a lowered or upper index is important, and it's a mnemonic, if you will. It's like for telling you whether you are differentiating with respect to something which has a raised index or lowered index. Okay, so the thing with the lowered index involves differentiating with respect to something with the raised index. The thing with the raised index involves differentiating something with the lowered index. Okay. All right, and the point is that this metric is going to turn out to be the Fisher information metric. Right, so the theorem is that the Riemannian metric in the exponential family is the Fisher information metric. And it's given by Gij is given by the expectation of the partial respect to I of log p x theta, partial respect to j of log p x theta. Okay. All right, so let me just prove that. Okay. So the proof is as follows. Okay, so we know that partial respect to I of log p x theta is equal to xi minus d sub I of phi theta, which is xi minus eta I. Okay, so given that, we have that the expectation of this expectation here Okay. Okay, so that is equal to nothing more than the expectation of xi minus eta I dotted with xj minus eta j. Okay, and this turns out to be, which is equal to the Hessian of the phi function, okay, which of course is how we go about constructing a Riemannian metric from the convex function. Okay, so this is the Riemannian metric derived from phi. Okay. All right. So that sort of wraps up this sort of abstract setting inside for the exponential family of probability distributions. Next thing I'm going to do is to show you a few examples of this. It's like which are sort of commonly seen families of distributions which you're probably familiar with, and then we're going to go off from there. Thank you.